up with calculus. Just a few more things to discuss about integration.
Sir,
Yes.
sir, will you take the doubts today at the end of the class?
Of what? Which part the doubts? The
Sir, you
calculus?
gave us homework for doing the module.
On the module now? Yeah, we'll discuss the doubts.
Okay,
For
sir.
calculus only, no? You mean?
Yes, sir.
Yeah, we'll start with that only. We'll wind up calculus now. So,
Okay, sir.
okay. So before we get straight into the doubts and discussions, just a couple of types of integration more that I wanted to discuss. Okay. So we have seen earlier in differentiation that if y is equal to tan inverse x, then dy by dx comes out to be how much? It comes out to be 1 upon 1 plus x square. How do we get this? By doing the chain rule application. We say that this implies that tan y is equal to x, right? So we say that differentiation of tan y with respect to x is equal to 1 on the other side. Okay. So this becomes by chain rule differentiation of tan y with respect to y into dy by dx. And that we know is sec square y. And then we continue that ahead. And we use the identity that sec square is equal to 1 plus tan square. Okay. And then we substitute from the beginning that tan y is equal to x. So we get dy by dx is equal to 1 upon 1 plus x square. So this gives us the direct relationship that derivative of tan inverse x is equal to 1 upon 1 plus x square. Now we will use that as a direct formula for integration. Okay. So if derivative of this function is this, that means antiderivative of this function is tan inverse. So integration of dx upon 1 plus x square is tan inverse x plus. So as of now, we can just see this as a direct consequence of this. But of course, this can also be proved by integration by substitution. But it should be like one of the direct formula to remember for integration. Okay, so just make a note of this first. Similarly, we'll discuss for some more integrals, like from the differentiation of sine inverse x, we will see how to integrate a couple of more things. Okay. So, till last time we have discussed about some methods in integration, like integration by substitution. And in that also we had seen two types of substitution. One was where we are directly substituting a linear term as a dummy variable, or another was where the quantity that we are integrating, that is of that particular type, that it is f of gx into derivative of g, that is g prime x dx. So that's a very specific type of substitution, and from that we had seen few examples of integration. Now today, we are just discussing a few special integrations apart from these substitutions, which will come in handy in our study ahead and in our derivations and things in physics. So you have to just keep a note of these special integrations that we're discussing. The first of them is this one, that integration of 1 upon 1 plus x squared dx is tan inverse x plus c. Yes, I mean, you don't have to note down all the steps because I'll be sending you the notes, obviously, but just make sure that you're clear with these steps and these particular integrations. Okay. So now this integral can also be done by substitution. If we want to do this by substitution, we will use a special substitution here, that in the integration of 1 upon 1 plus x square dx, we use a trigonometric substitution, wherein we substitute x as tan theta. So this is our dummy variable. So the reason why we do this substitution is that we make use of the identity that 1 plus tan square theta is sec square theta, and we also make use of the derivative, that derivative of tan theta is sec square theta. So is to take advantage of these two properties that these functions have. Okay. So once I substitute x as tan theta, so what happens is the denominator simply becomes sec square theta, that you can see from here. So this is one thing we'll substitute, and dx by d theta is differentiation of tan theta. So that's sec square theta. That means we can substitute dx in the numerator as sec square theta d theta. This is the second thing we can substitute. So in the original integration, we will substitute this thing. We will substitute the numerator dx as what? Sec square theta d theta. And the denominator will be substituting as 1 plus tan square theta, which also becomes sec square theta. So we are just left with this. So that's what makes the integral easy to solve. So this is theta plus c, because now theta is the variable. And now we have to resubstitute. So how we'll resubstitute? Tan theta was equal to x. So that means theta is equal to what? It is tan inverse of x. So we can see that finally the integral becomes, or the antiderivative becomes, tan inverse x plus c. Okay. So this you can say is like a proof of this integral that we've seen before. Now the reason why we are discussing the substitution method, obviously you'll remember it as a direct formula, but in case there's a bit of variation in this, we can still use the substitution. So I'm coming to that. So think of this like a basic integral, and this is like the proof of this. Okay. Okay, so hope this method is clear to all of you of the substitution. Right? So just think of it like a special type of substitution. Like we have done substitutions of two kinds in the previous lecture. Now there is another type of substitution called a trigonometric substitution. It's a very specific type of substitution, and this is how we do it. Okay.
Yes.
So now let's see a variation of this. Okay. So instead of, suppose we have an integral like this. Suppose we have integration of dx upon a square plus x square, where a is any constant. A is just a constant, so it's a number. So for example, instead of this, we have dx upon 4 plus x square. So you can see that 4 plus x square we can write as 2 square plus x square, like that. Okay. So then what we do is we use the trigonometric substitution. That x is this time, instead of tan theta, it is substituted as a tan theta, so that we can still make the denominator in terms of 1 plus tan square theta. So the denominator, which is a square plus x square, becomes a square plus a square tan square theta, which can still be expressed as a square sec square theta. So this is the logic of doing this substitution. And then of course, dx by d theta is the derivative of a tan theta. A is just a constant, so it's a sec square theta. So that means in the numerator we can substitute dx as a sec square theta. So these two things are now substituted in the integral. So the integration, which was originally dx upon a square plus x square, now becomes dx is replaced with a sec square theta d theta, this thing here, and the denominator is replaced with a square sec square theta. So 1 by a is just a constant, it comes outside. And again, we have the same kind of thing. Okay, so now we again resubstitute this, same step exactly. So you can see that it's the same process. That additional constant a square doesn't provide any problem for us now, because we are just incorporating that by taking x as a tan theta instead of taking it as just tan theta. So that's like a trick that we are using, a manipulation trick. So now we have to resubstitute this. So our x was equal to a tan theta. That means tan theta was equal to x by a. So that means theta is how much? It is tan inverse x by a instead of tan inverse a. So the integral is now becoming 1 upon a tan inverse of x by a plus c. And you can later verify that this is the correct antiderivative by just taking differentiation of this. So later when you're revising these notes from today's lecture, you can just do it as a differentiation exercise now, that the reverse of it. You can just verify this later, that if you differentiate this term, you will in fact get this term. Yes, that means this is the correct antiderivative of this, along with the constant, of course.
So,
Yes.
so how did that x equal to a tan theta came?
No, that is the substitution that we have done. Okay, so this is a dummy variable that we have introduced. So that is up to me. ना मैं तो कुछ भी substitute कर सकता हूँ यहाँ पे for just taking advantage of an identity, right?
But sir, how did that tan theta come?
That's the dummy variable, no, beta. Theta is the dummy variable.
Okay, sir.
So I'm making, like, instead of substituting something of x as z, no, I'm substituting x as something into tan theta. So theta is my dummy variable. Understood, no?
Yes, sir.
Okay.
So, sir, in short, we are telling that a tan theta is the whole as dummy variable.
Yeah, matlab in that basically theta is the dummy variable, but like we are substituting x as a tan theta. Understood, nothing? Like x is a variable, like that theta is also a variable. So what is the relation between the variables? That x is equal to a tan theta. So in that, theta is a variable that I have introduced to make the problem easier. So it's what we call the dummy variable.
Okay, sir.
So that's why we call this type of substitution as a trigonometric substitution, because we have substituted x in terms of a trigonometric function of the dummy. The tan theta is a trigonometric function of the dummy variable theta. Now the difference is, in the first one we did the standard form, it was dx upon 1 plus x square. So we substituted as x as just tan theta. Here it's dx upon a square plus x square, where a is any constant. So that's why we are now substituting x as a tan theta instead of tan theta, so that we can get rid of that a square in the denominator. Yes.
Sir, I got the sum, but sir, how to know that we have to take that specific a tan theta only as the dummy variable?
So that is the thing. Now you see in the denominator there's a square plus x square. So if I substitute x as a tan theta, I can simplify it like this now, because 1 plus tan square theta is x square theta. So that is the reason why we are doing the manipulation. Now it's a manipulation, but always behind manipulation also there's some logic. Now we don't do it randomly. So यहाँ पे logic क्या है उसका, that a square plus x square को simplify करना है. So how we'll take advantage of that identity that 1 plus tan square is x square, by taking x as a tan theta. So that a square comes common. Got it now?
Yes, sir.
Okay.
So,
yes.
what if we use it in the formula?
Which type of formula, beta?
So the same formula which you gave above for integration of
No,
trigonometric.
we can't. So we can't see directly use this in the formula, no, because the formula was for what? It was that differentiation of tan inverse x is 1 upon 1 plus x square. But we have that extra term of a square, no?
Yes, sir.
You got my point, no? So we can't use this directly, no?
Okay, sir.
That's where the manipulation comes in, no? See, iska inverse kya hai? That integration of a 1 upon 1 plus x square is tan inverse x. But here in the second one, we had in the variation one, we had the extra term a square in the denominator. So how we took care of that problem, that there's the extra term a square, by just doing a small manipulation, that instead of substituting x as tan theta, which is the standard one, in the variation one, we are substituting it as a tan theta. Got it, no?
Got it, sir.
Okay. Okay, now another similar kind of trigonometric substitution that we use is this one. So we know that if y is equal to sine inverse of x, okay, then dy by dx comes out to be 1 upon square root of 1 minus x square. So again, how this comes like this, that y is equal to sine inverse x implies that sine y is equal to x. So again, apply that differentiation on both sides. Again, apply chain rule. So we have now differentiation of sine y is cos y. This now tells us that dy by dx is 1 upon cos y. I want to reduce it in terms of x, and x is what? Sine y, or y is equal to sine inverse x. So how we'll reduce this? Cos y can be written as square root of 1 minus sine square y, which can further be written as. So that's how we get dy by dx is this, or that differentiation of sine inverse x is given by the formula 1 upon square root of 1 minus x square. So now you can see that the reverse of this is that integration of 1 upon square root 1 minus x square dx is equal to sine inverse x plus c. So this is a second integration which is coming from the formula of differentiation of inverse trigonometric functions. Okay. So again, this is a standard integral that we should remember from now. And the logic of this integral one can understand from this simple differentiation. Now this integration can also be done similarly using a substitution like we have done earlier. Okay, so let's understand this integration also by substitution, and then we'll see the variation of this one also. So here, what we do is to take advantage of the identity that sine square theta plus cos square theta is equal to unity, and that the derivative of sine theta is cos theta. So take advantage of these two things from trigonometry. We make use of this substitution that x is substituted as sine theta. So the denominator then becomes just cos theta. So square root of 1 minus x square becomes cos theta. So the numerator will come by differentiating this. So now the numerator, which is dx, can be substituted as cos theta d theta. So the denominator is substituted as cos theta and the numerator substituted as cos theta d theta. So the integration becomes again just theta. And then again we resubstitute. We had x equal to sine theta. That means theta is sine inverse x. So that's how we get this, that this particular integration comes out to be sine inverse x plus c. So you can note down the substitution or work out the steps and then try the variation yourself. Now the variation of this is like this, that instead of this, if we have the integral square root of e square minus x square, where e is any constant, then how we will find this integral? Okay. So just if you like try to apply the same kind of trick that we used in the variation of the tan theta, I mean tan inverse x integration, you will realize that you can try something similar over this here also and find out the integration. So just try to relate the steps from there or relate the manipulation from there and work this out yourself. I'll put up the solution in a minute. Yeah, so okay, very good. Very good, Parv. That's correct, in fact. So I'm just giving you the first step for those of you might not have started this integral. The first step is, see here, to get rid of this a square term. We take advantage of again that identity that 1 minus sine square is cos square. But then there is also this a square. So we'll substitute trigonometrically that we substitute x as a sine theta. So then what happens is that this term a square minus x square becomes a square minus a square sine square theta. Becomes a square cos square theta. So therefore we can substitute the whole denominator as a cos theta. Now try to complete the steps yourself. The rest of you, everybody also. Right. So let's complete this now. So dx by d theta, we can see from here is differentiation of sine theta. So that's a cos theta. So a numerator which is dx will become a cos theta d theta. So you can see that this time when we substitute in the integral, we get just integration of d theta. That is theta plus c. Now for theta, to resubstitute it, we'll have to understand that we have substituted x as a sine theta. So that means sine theta is x by a, which means that theta is sine inverse of x by a. So finally, the integration or the antiderivative of this becomes and again you can verify this later by doing differentiation by chain rule. Okay, so these two are a couple of important trigonometric substitution integrations to remember. Okay. Then one more important trigonometric identity that we make use of is the formula of cos 2 theta or cos 2x. Now this can also be manipulated into 2 cos square x minus 1 or 1 minus 2 sine square x. So now if we reverse this identity, then we can also from this understand that cos square x can be written as 1 plus cos 2x, the whole thing divided by 2. And likewise, sine square x can be expressed as 1 minus cos 2x, the whole thing divided by 2. So these two identities now are very useful in doing integration. So we have an integration of cos square x. We can solve it by expressing it as this first, and then breaking the integral into two parts. And then just using the simple idea that the integral of cos 2x will become sine 2x by 2. So there's another 2 here. So simple logic of that is we know that integration of cos x is sine x. So that linear substitution thing that we had seen earlier. In general, that will be like this. So specifically, integration of cos 2x is sine 2x by 2 plus c. So that's what we are making use of over here. So I'll just leave you to make a quick note of this integral. And most importantly, this identity. Okay, now similarly, you can also understand if we had integral of sine square x, we'd use the same kind of identity. We'd express sine square x from here as 1 minus cos 2x. So it just makes a difference of 1 minus sign, rest is exactly the same. So another two important integrations for us. Okay, so let's practice these integrals a little bit in context of definite integration also. Okay, so just try out these three integrations. Yeah, okay, Yashwardhan, I'll scroll up.
Yes, sir.
This one, the cos square and sine square. Okay, okay, yes. Yeah, now try out these integrations. We'll discuss in a few minutes. Yes, good Manav. Now you have to put the limits in that. Okay, you have got the like the antiderivative correctly. Now you have to put the limits from x equal to -4 to +4. Okay.
Yes, sir.
Sir, can you scroll up for a second?
Scroll up to what, that cos square sin square integration.
Ah, yes, sir.
Okay.
Okay, sir. Thank you.
Okay, people, let's check out the answers. It's not the question of interval. Okay, it's the question of the limits. Now we have to find the antiderivative there and then put the limits in each of these parts. So it's not really about the interval. So anyway, let's look at the first one. So we can solve the integration by either doing substitution or directly applying a formula. So here I'll do substitution. I'll substitute x as 4 tan theta. So dx will become 4 sec square theta d theta. So the integral will become 4 sec square theta upon 16 sec square theta from x equal to -4 to x equal to 4. So that will be 1 by 4 theta, or just do it step by step, to integration d theta now the limits are in terms of x, so we have to replace theta properly. So finally, replacing theta in terms of x, you can see that tan theta is x by 4. So that means theta is tan inverse x by 4. So the integral is 1 upon 4 tan inverse x by 4 plus c. There is the antiderivative. Now we have to put the limits. So this will become 1 by 4 into tan inverse of upper limit will become 4 by 4, which is 1, minus tan inverse of lower limit, which is -1. It's -4 by this. Now tan inverse 1 will be pi by 4 or 45 degrees, and tan inverse -1 will be minus pi by 4. So as you can see, this will become so pi by 8. That will be our answer. So here we have to understand that we know that tan pi by 4 is equal to 1. So that means pi by 4 is tan inverse 1. Okay. And we know that tan of minus pi by 4 is -1. So these two values we are using here.
So why are we taking like minus pi by 4 instead? Like 3 pi by 4 can also be taken, right?
It's like this, that tan inverse function is defined in the like primary domain, from minus pi by 2 to plus pi by 2.
Okay, sir.
Because it's the inverse trigonometric function, that's why.
So that was
okay.
what I was asking, that which value will we have to take?
Okay, so I'll just scroll up a little so that we can go through the other questions. Okay. After completing these 4 problems, we'll be discussing the doubts from the module. So just be ready with whatever questions you want to discuss. Any question from any of the exercises of calculus module? Second one, anybody got the answer? You've done the integration earlier, sine square x, the indefinite integration. Now to just put the limits. Upper limit is pi and lower limit is 0. Just see what we'll get from it.
So 0 is the answer?
No, sine square x dx, but the integration will not be 0. See, there is that x by 2 term, no? See the integration?
Yes, yes, sir,
So
yes.
that x by 2 term will not allow the answer to be 0, no?
Yeah, yeah.
Yeah, so anybody got the answer for the second one?
Yes, sir. Like I saw that.
Yeah, how much is the answer?
So it's in terms of pi. 2 pi by 4 I got like pi by 2.
Yes, 5/2 you got now?
Yes, sir.
Good. Now the third one is very similar, but there is that extra term pi inside. No? It's like cos square pi into t. T is the variable, pi is a constant. Okay, so I'm just completing the second one for those who have not worked it out yet. Sine square x integration from 0 to pi. So we use this identity that cos 2x is 1 minus 2 sine square x, or sine square x can be written as 1 minus cos 2x whole divided by 2. Now break it into the two integrals. So this is the antiderivative, and on this we'll put the limits 0 to pi. So the upper limit you can see will become pi by 2 minus sine 2 pi by 4. C will anyway cancel out, and the lower limit will be 0 minus sine 0 by 4. So that will just give me pi by 2. So that's how the answer is just coming out to be pi by 2. Okay. And it will obviously make sense that we should get a non-zero sort of value, because sine square x graph you can see is going to be a graph that is always above the y-axis. I mean above the x-axis. A graph like this, it varies continuously between 0 and 1.
So,
Yeah,
so for sine square x, if we take 1 minus cos square x, so will the sum happen?
you can't solve it further. No? Substituting sine square x as 1 minus cos square x, like it's not going to help you in doing the integration. But substituting sine square x as 1 minus cos 2x whole divided by 2, that's what helps us in doing the integration. You understanding?
Yes, sir.
We can substitute it as 1 minus cos square x. There's nothing wrong with that substitution. It's technically correct. But we can't solve the integration using that substitution.
Okay, sir.
So this is the area we have calculated as 0 to pi.
Sir, C1 का answer is like 1. No, it's 3 questions. Answer is 1.
That cos square pi t1.
Yes, sir.
Yeah, the answer is 1. That's correct. Good.
Okay.
It was 1 to 3. No, the limits was p equal to 1 to 3. No?
Yes, sir.
Yeah, the answer will be 1.
Okay.
Okay, and now just work out the fourth one also. Okay, now people, as we complete these 4 questions, also be ready with the doubts of from the module. We'll discuss that next. Okay, good, Manav. That's correct for the 4th one also. Okay, so now I'm working out C and D. So we'll use the same trick in this one. We'll use a trick that cos square theta is 1 plus cos 2 theta divided by 2, because cos 2 theta is equal to 2 cos square theta minus 1. So here just think of theta as pi t. So this becomes 1 plus cos 2 pi t divided by 2. So this is not d theta, this is obviously dt in the integration. Right, so the next step, we just expand this. This becomes 1 plus cos of double of what was here, pi t. So 2 pi t, the whole thing divided by 2 dt. I'm going to just skip one step and do the integration directly. So we have 1 by 2 is the first term. So its integration with respect to t will become t by 2. Okay. And then we have 1 by 2 outside and cos 2 pi t. So its integration will become sine 2 pi t divided by 2 pi. And there was one extra 2 outside. So this is the indefinite integration. So this is from t equal to 1 to t equal to 3. So I skipped a couple of one step over here. Try to make sure you figure out the step yourself that I've skipped. Okay. So now you put the limit. So the upper limit is 3 by 2 plus sine 6 pi t. Sorry, 6 pi by 4 pi, minus the lower limit is 1 by 2 plus sine 2 pi by 4 pi. Okay. So it's 3 by 2 minus 1 by 2. That's how it comes out to be 1. So this is also an interesting graph if you think about it. The graph of cos square pi t this sort of a graph. Varies between 0 and 1. So now this is the total area that we are calculating from here to here. This shaded area that I've shown you, this area. Okay, let's finish the final one. So here, you know what we have to do. We have to substitute x as 2 sine theta, so that the whole denominator becomes 2 cos theta, and the numerator becomes also 2 cos theta d theta. So the integration, just the indefinite integration, becomes sine inverse x by 2 plus c. So now this integration with the limits becomes sine inverse x by c plus c. So x by 2 plus c. On this antiderivative, we have to put the limits x equal to 0 to x equal to 2. So the upper limit will become sine inverse 1 and the lower limit will become sine inverse 0. C anyway cancels, so we need not write it also. Now sine inverse 1 is pi by 2 and sine inverse 0 is 0. So your answer is pi by 2. Okay, so people, hope these questions are clear to all of you. Now let's move on to doubts from the module exercises. So basic calculus exercise 1, 2, 3 and 4. Any doubts if you have, please let me know or drop a text message. Let's start with doubts if any from exercise 1.
Sir, in exercise 1, section 490.
19. Okay. Start with that. So this one, differentiation of 1 by 4 tan to the power 4x, that one.
Sir, integration of
Oh,
x.
Exercise 1 section,
Sir, just
or is it exercise 2?
sir, section 4,
Section 4, question number
19th.
Question number 19. Achha, can you just read out the question to me?
Sir, integration of x divided by x square plus a square.
Okay. Okay. X divided by x square plus a square. Okay, so this is exercise 2, no matter, or is it exercise? Achha, maybe I'm having some older version of the booklet. Anyway, so in my booklet, this is exercise 2, question number 19. I don't know why there's some confusion with that. It's on page number 40 in my booklet. Same question, question number 19, but it's of exercise 2 in this book. Page 40 of the module. Yeah, so see what we can do in this question. This is a question of this type now, that you notice that you have x square plus a square in the denominator and you have x in the numerator. Now, if you think of x square plus a square like a function, what is the derivative of that function?
Yeah, sir, actually, I just noted it wrong. It's actually exercise 2.
Okay. So exercise 2 only, no? Yeah.
Yes, sir.
That's what I thought, okay. Because should not be anything. Yeah. Yeah, so now think what I'm saying. If you think of x square plus a square like a function, what is the derivative of that function?
X.
2x.
2x.
Sure,
Yeah.
2x.
But we have x in the numerator, no? So if I multiply,
Yes, sir.
divide by 2, it will take care of that. So it's that kind of substitution. Understand? No? So if I substitute this denominator, x square plus a square as a dummy variable z, okay, then what will happen? Dz by dx is 2x. So cross multiplying, I can write x dx as half of dz. So I can substitute this thing and I can substitute this thing. So the integral now becomes what? It becomes half comes outside dz by z. So it is 1 by 2 ln z plus c. And then we have to remove z from the answer. So resubstitute it as x square plus a square. Okay, so we can leave the answer this way also, it's correct. Okay. Or we can also take the half inside the ln using the property. So it will become ln of square root of x square plus a square. So depends on how the answer is given in the options. Okay. So last step, we are just using this property that n times ln a is ln a to the power n. Okay, this is clear now?
Yeah, sir.
Okay. So they have given the answer as this one. They have given the answer as this one. But you can also reduce it by one step to this. Okay, any other question? Anybody has any doubt in exercise 1? Okay, good. Exercise 2, any other doubt? Okay, next exercise 3. Exercise 3 are those word problem type questions. Have you done these questions in exercise 2 in the last page, like 23, 24? These are all quite tricky problems. I think let's discuss few of them.
Yeah, sir.
Okay, so I'm going to put some questions that we'll do as a class exercise from the module only, from exercise 2. Because some of these integrals are a little bit tricky. Okay, so all of you please turn to page 41 and do these, try out these questions. 21, okay, then 23, 24. And 25 and 26. These questions we'll quickly discuss. And meanwhile, if you have any doubt in any of the exercise 3 problems, please let me know or drop a message. We'll discuss that also. Okay, Jitesh, you can verify your answers also. Okay, what about 21?
I'm trying that.
Okay. So 21, the hint to you is again use the cos half angle formula. Just like we can express cos 2x in terms of sine square x or cos square x. Like that, we can express cos x in terms of sine square or cos square of x by 2. So that cos 2 theta formula, you can use a manipulation of that to get rid of 1. Okay, so people for 21, I'm again just reiterating the hint that you can use. Because we have the formula that cos 2 theta so therefore cos x can similarly be written as 2 cos square x by 2 minus 1, or if required it can also be written as, now in that particular question in 21C, if you just use this, you get rid of 1 inside the square root.
So for 21 is the answer 2.
Check out in the this thing. I'll just calculate and verify for you. Okay. No, I think it will be root 2 comes out, and then we have I think it will be 1 if I'm not mistaken. Because when you substitute x na, in that sign term na, inside the bracket you have x by 2 na, so the upper limit will be pi by 4 when you substitute x as pi
Yes,
by
sir,
2. You understand me?
but it will be sine x by 2. So like we will do that sine x is equal to then ax plus 2, ax plus b we did now. Substitute
That will also
so the,
yeah, so the
for-
answer is 2.
yeah.
The answer is 2. Good. Okay, so I'm just working out the steps for question 21 for everyone. So again, it is about making use of this identity. The cos 2 theta formula. It can be manipulated in many ways, this formula. So for example, instead of this, if I had this integral also, square root of 1 minus cos x, then also I could have made use of this kind of identity. This is question 21. This is another example. Now in this, I will substitute cos x as 2 cos square x by 2 minus 1. Whereas in this, I would have substituted cos x as 1 minus 2 sine square x by 2. So on doing this substitution, this one becomes zero to pi by 2 root 2 of cos x by 2 dx. So the root 2 comes out, integration of cos is sine, but there is a coefficient of half. So that comes in the denominator. So this is your antiderivative, and these are the limits. So this is actually 2√2 sine x by 2 plus c from 0 to pi by 2. Is this correct?
Yes, sir.
Upper limit ये हो जाएगा, right? And lower limit will be sine 0. So that will give me my answer as 2. Similarly, you can work out this integral also later. There's another example. So whether we have this or this, we can make use of this. Okay. In fact, even if we have sine, even then we can do this. Square root of 1 plus or minus sine x. Like suppose we had 1 plus sine x. We have two options here. One option is we can write this as 1 plus cos pi by 2 minus x. So now you treat this thing as 2 theta. So cos square theta by 2 minus 1. That's one option we have. Another option we have is that we can also write this as this, okay, and then we can expand the 1 as sine square x by 2 plus cos square x by 2. So these are a few more manipulations of the similar type.
So,
Yes,
sir, actually, I have a doubt.
yes, Beta, tell me.
Sir, I have sent you on WhatsApp.
Okay, just a moment, I'll go through it.
Yes, sir.
Okay. Now you can also understand that why these two are actually identical terms. This one that we've got, this is identical to this, because if you just expand this by the formula no, of cos A minus B, you will see that it comes out to be this with the root 2 outside also. So we can express a term like this as either this, or we can express it like this and then integrate it if required.
Yes, sir.
Couple of more manipulations you can note down apart from just question number 21's manipulation. So these half angle formula or double angle formula, whatever, they're very handy. Okay, this one and even this one, that sine 2 theta is 2 sine theta cos theta. So both of these are very handy formula. Okay, now really don't need to worry too much about lot of manipulations right now in basic calculus, because physics we will not get problems that are way too complicated in terms of manipulation. But when you come to advanced calculus in 12th maths, you will learn a lot of these techniques and you'll have a lot of practice, so you get used to these things. Whereas if you just keep in mind the ones that I have discussed in class, then at the physics level you will not have difficulty. Yeah, this cylinder problem, no, we'll discuss this. This is from your major test.
Yes, sir.
Yeah, so this is a problem of maximum minima. Okay, it's a nice problem. Okay, this was probably the only tricky problem in calculus I had given in this major test. I mean, some of the questions were lengthy and all, but this was the one which was little extra tricky. Okay, let's move on to question 23. Now 23 is also a similar type of manipulation like the one I told you we can do here. Like a couple of different ways we can manipulate it. Actually, one is, in any of these questions, as far as indefinite integration is concerned, if nothing else is striking, you can check the 4 options and differentiate them. So you go in the reverse order that, if you check that the differentiation of one of the options is giving you the quantity in the integration, that means it's the antiderivative. So at an exam level, you can use that as an elimination method also. But here what we'll do is, one method is that 1 upon sine square x into cos square x can be easily written as sine square x plus cos square x upon sine square x cos square x. So that will become 1 by cos square x plus 1 by sine square x. So that is sec square x plus cosec square x. Okay. So using this simple manipulation, okay, I can simplify this integration to sec square x plus cosec square x dx. Okay. And now I also know that the differentiation of tan x, the differentiation of tan x is sec square x. So the integration of sec square x should be tan x. And I know that the differentiation of cot x is minus cosec square x. So the integration of cosec square x should be minus cot x plus. So next I make use of these two. I mean these two formulae here to understand that this integral will become tan x minus cot x plus. Okay. And if that is by chance not matching any of the options, here it is matching, then you might also have to simplify this, okay, by just expressing it this way. In this case, luckily that's not happening. We're not having to simplify it that way. But this also has another very interesting simplification. You can also now further write the numerator as minus cos 2x, right? And the denominator as sine 2x by 2. So this in fact becomes minus 2 cot 2x. Is that correct? You can see there are so many different ways we can express the answer. So that's where the whole subject of antiderivative and indefinite integration is a very tricky one. This much tricky things are not there in physics, don't worry, okay, because we are always going to use it in solving application problems. But when it comes to advanced calculus in maths and 12th, you will see that it's something which is a little bit like algebra. A lot of practice, a lot of like systematic manipulation methods and all are required. So this is one way of doing the question. Another way of doing the question is that I can write this as this. So that is this. Okay. So 4 upon sine squared 2x. So that is 4 cosec squared 2x. Okay. So I can also write this function as this. Okay. Now you'll see the thing is, like, if you had started this way, it would take you a lot of effort to come to this answer, but you would come to this answer directly. Okay. Let's see how. So again, that's the tricky thing in integration, that sometimes, you know, when we use one method, it takes us a lot of manipulation to come to the answer in one form. If we use the other method, it might be easier to come to that manipulation. Okay. So anyway, so this is becoming 4 cosec square 2x plus c. Now we'll use this thing. So this will become minus 4 comes outside, and cosec integral, I mean, is cosec integral is 4 comes outside, and cosec integral is cot, but it's cot of, or rather minus cot, divided by the coefficient of this. So you can see you're coming to this answer very easily by this method. Okay, but now from this answer to get to this one is going to be a very long process. So, you know, if the answer is given in this tan x minus cot x form, it was just a lucky break for me that I used the sec square x plus cosec square x method. If I'd used this one, then it would have taken me a lot of time. Sorry, this one is not plus here, it's multiplication. But as I said, like at this stage, you need not worry about these extra lengthy kind of things. Like whenever you come across something, treat it like something as a challenge to learn, and like put some thought and effort into it. Still, if you're not getting it, ask me for a hint, or you can discuss among yourselves also, or during the mark sessions and all that. But don't panic about anything. Okay, as long as you are clear with the basics of integral, like you can calculate the area under the curve for a parabolic graph or a simple sine cos graph and all that, you will not have difficulty at the level which is the aim right now, that solving physics problems using calculus. That will not be a difficulty.
Yes, sir.
Okay. Yeah, Yash, I have received your doubts for exercise 3 also. Let me see if I can come to that today. Otherwise, I will send you some hints separately. Now, next we have to do question 24. 24 is a relatively easier one. You have to just take this one step further. Okay. Now you notice that if you take this as your dummy variable, you substitute this, then dz by dx is e raised power x itself. So your numerator becomes dz. So your integral becomes dz by z, which is and again, this is one question which we can have done very easily by working backwards from the answers also. If the forward method is not striking you at the moment, you can just like it will just take a little bit of time, maybe a couple of minutes, but you can just differentiate all 4 options and see which one is the correct antiderivative.
So plus the options were also like very different, like only E term in one option, like and all were trigonometric.
Yeah, it was pretty obvious that those options with tan and cot cannot. Okay, so I think those options are a misprint because they are the same as the BCD options in question 23. Those options should have been more like ln of 1 minus e raised power x, ln of 1 plus. So just change the options. But now it doesn't matter. We have done the question, but I think option B was supposed to be ln of 1 minus e raised power x plus c. Then option C was supposed to be ln of 1 plus e raised power minus x plus c and all that. So these kind of options. So you just have to put a little bit of effort to differentiate them if you're going by the backwards method. Okay. So again, nothing terrible. Okay. Then 25 is again very similar. You notice that differentiation of cot x is minus cosec square x. So that minus that cosec square x term is already there in the numerator. You have to just supply the minus sign. Okay. So I will just tell you the substitution. You can complete this problem yourself. If you substitute 1 plus cot x as z, then cosec square x dx will be substituted as minus dz. So your integral will become minus of dz by z, or minus ln z plus c, which you can also write as ln of 1 by z plus c, or whatever, and then substitute z again as 1 plus cot x. Okay. Okay, and then 26th sum is also simple. Once you get the idea of it, that how we have to do this. So notice that basically 1 by x is the derivative of ln x. So if you substitute ln x as z, so dx by x will become dz. So your integral is just becoming z dz. Again, this is one which you can also do by going backwards. Differentiate all 4 options and see which one is giving you. Okay, now I'm coming to that cylinder question from your major test paper. That rod which was expanding into a cylinder. That this question where an object which basically looked like a thin cylindrical rod initially. So its thickness is tending to 0. Now it was gradually expanding. Okay. So after some time, it would be seen as a cylinder whose length has become less than the original rod, but at the same time, whose cross-sectional area in the form of the circular cross-section that is increased. That's continually increasing. Okay. So this was the situation of the rod at time t equal to 0. So its length was L0 and its thickness was negligible. So we'll say it's tending to 0. Now at some time t, the length L had become L0 minus some factor. So all these values were also given to us, but just let me refer to the question. So this was L0 minus alpha t, whereas this radius, it had expanded to some factor beta into t, where all these values were given to us, that L0 was 12 meters. Okay. Alpha, the rate at which the length is decreasing, was equal to 4 meters per minute. And beta, the rate at which the radius is increasing, is half a meter, 0.5 meters per minute. So what we'll understand is something very interesting here, that initially what was the volume? It's tending to 0 now, because it does not have any thickness. But right now at time t, what is the volume? It is pi r square L. Okay, and eventually after some time, what is going to happen? This is going to now the length will tend to 0. So it will basically become a disk. So again the volume will become 0. After sufficient amount of time, you will see that this is how the object looks, because its length was decreasing. You can even calculate after how much time this exactly happened. The length is going to tend to 0. So it's L, it's tending to 0. It's having the maximum radius at that point of time. But now the volume will again be 0. So basically you can understand the behavior of volume with respect to time is something like this, that it starts from 0. I don't know what the graph is like, but eventually it's becoming 0. So in between somewhere it must be reaching a maximum value. So it's ultimately a question of maximum minimum. And you can see how to solve it as a maximum minimum problem, because now when you substitute R as this and L as this, you can see that your volume is a cubic function of time. So you know how to find local maxima and minima and all that. So all you have to do is express it. V is equal to pi beta squared t square into L0 minus alpha t, or it is pi beta square L0, which is a constant, into t square minus pi beta square alpha, which is again a constant, into t cube. Okay, so it's like this kind of a thing. It's like, AT square minus BT cube type of function, where A and B are these constants. So now I want to find the maxima of this. Okay. Maxima between t equal to 0 to t equal to this time, let's say it's capital T. So that is the time when volume becomes 0. So that time you can see is equal to L naught by alpha. So that's when the length will become 0. Okay, so it's ultimately that simple a problem. It's just a matter of figuring out like what we are trying to do in the question. Once you reach this step, now you got volume as a function of time, you'll realize it's a very simple problem. So volume is this kind of function of time. Okay. And we have to find the maxima, and that too not for the entire domain. Okay, we have to find the maxima between just these two times. Because obviously volume cannot become negative. No? So between t equal to 0 to t equal to capital T, which we have seen is L naught by alpha. So in just this range of time, what is the maxima it reaches? So you'll realize that we've done enough work with cubic functions for you to be able to figure this out quite easily, that there is one local maxima point in between. Now, if you look at this cubic function, this function of this type, AT square minus BT cube. So I'm not working out the whole thing here, okay, where A is basically this thing. It is pi beta square L naught, okay, and B is this thing. It is pi beta square alpha. Okay. You'll see that this volume versus time, if you were to just plot it as a graph, generally speaking, it would come out to be a graph like this. It would have one local minima at 0, another local maxima at this point. So you'll get two turning points. Okay. But for us, which part of the graph is important? Only the part of the graph which is between here and here, because volume cannot actually be a negative quantity. So the rest of it is just a guideline. Okay. For us, only this section is important, between 0 and this time. And in this section, we'll get one particular value of time, let's say T1, at which the volume is maximum. And that's what we have to calculate. Okay. So you put dV by dt equal to 0. So you're getting 280 minus 3bt square as 0. So you'll get two roots. So you see t equal to 0 is one root, but that is this one. So we won't take this one. You get 2a by 3b. This is the correct one. This is the one T1 that we have shown in the graph. So this is the time at which volume reaches maximum. Okay, Om, so hope this question is clear. At least the method for it is clear. You can try it from this point onwards yourself once.
Yes, sir.
Okay, give it a try and see if you'll get the answer. I think the answer will come out to be 8 if I'm not mistaken, 8 or something like that. Just let me check and tell you.
Yes, sir.
Okay. Yeah, the value of time you will get in this in minutes, at which there's the maxima is 2 minutes actually. The answer will come out to be 2 minutes at which this is reaching the maximum. So when you calculate
Yes,
this
sir.
2a upon
Because-
3b, putting all these parameters, you will get the answer as 2 minutes. Okay. So the answer in integer type should be 2. Okay, so we will conclude here today. Yes, I know you have a couple of questions from exercise 3 pending. If you can just drop me a message on WhatsApp about those questions, I will give you some hints, and if required in the next lecture, we'll discuss it. Okay. Or the next time we have a mentorship session or something, we'll discuss it. Okay. Okay, people. So that's it for today's session. Make sure you revise today's session, the special integrals that we've done, the 2 or 3 trigonometric manipulations and trigonometric substitutions. Okay. Just keep them noted down as tricks that we can use in certain types of problems in future. And also start working out the questions from exercise 4 if you haven't, the kinematics applications, because that is what we will start with in the next lecture actually. Application of kinematic calculus is going to be the beginning of the study of kinematics for us. Okay. We also have another board level lecture coming up this week in which we'll study one-dimensional motion and projectile motion. So I
Sir,
think
I have done
is,
that exercise 4.
Okay, very good. So
Sir,
you can
main
like
part is integration only in that.
so you can continue ahead and start reading the kinematics chapter, no? In the same module, the one after this.
Yes, sir. Okay, sir.
You can go ahead with that. Okay,
Thank
that's
you.
it for today,
Bye,
people.
sir.
Yeah, yeah. Wish you all the best.
Bye, sir.
Bye, people.